In this section, we will see exponential model, logistic model, or logarithmic model. So we will use our exponential log function in our real life situation. Okay. So let's start with a function with an example here. It takes 29 years for an initial amount of strontium 90 to break down into half the initial amount, which is A naught over 2. Okay, so here we have A naught. This is the initial amount of strontium 90. This is one of the element, okay, earth element. And it takes 29 years. Okay, so you have A naught as an initial amount of strontium 90, and after 29 years, that strontium 90 break down into half, break down into A naught over 2. Okay, that is half, which we call half-life of strontium is 29 years. So you have any element, okay, and the time it requires to decay or to break into half is our half-life. We call it half-life. Okay, so this is an any element. Okay, it can be like a radioactive element. So if you have like a 50 milligram of strontium 90, then after 29 years the strontium 90 will be half of 50, so there will be 25 milligram. It means 29 is the time required by strontium 90 to break into half of its original amount. Okay, so given an initial amount A naught, so our A naught is the initial amount, grams of strontium 90 at t equals to 0, find an exponential decay model. So here we have the exponential model, exponential function that gives the amount of strontium 90 at a time t. Now here what we are asked to find, we are asked to find exponential decay model. Okay, so we are asked to find A of t equals to A naught e to the power k t. So we have to find what is k here. Okay, we have to find the value of k in this model, and we can use this model, or we can use this function to find the amount of strontium 90 at any time period. Okay, now what do we know from our very first statement? So from here we know that 29 year is the half-life of strontium 90. Okay, so let's take our t equals to 29. So when our time is 29 years, okay, so when our time is 29 years, what will be the amount of, this is the amount of strontium 90 after t years. Okay, so if our t is 29 years, what will be the amount of that strontium 90 in 29 years? So let me replace that t by 29. Okay, so if our t is 29, then A of 29 equals to A naught as it is e to the power k, t is 29. So from the very first statement, so strontium 90 is an element. Okay, so that element takes 29 years to break it down into exactly half. Okay, for example, as I said earlier, if you have like a 20 gram of strontium 90 now, okay, now after 29 years from today, that 20 gram will be 10 gram. Okay, it will be exactly half after 29 years. Okay, that's the property of that strontium 90. Now, our time is 29 years. Okay, so if our time is 29 years, what will be the amount of that strontium after 29 years? it will be exactly half of what we have in what we have during our original time. Do you agree? So our A naught, okay, so here we have A naught as the amount of strontium. That's the original amount that we have. Okay, so we have A naught amount of strontium 90. Now after 29 years, what will be the amount of the same element after 29 years? A naught is the amount of strontium. That's what we have right now. Okay, so we have A naught. Now after 29 years, what will be the amount of strontium? Half, right? It will be exactly half. So what is the half of A naught? A naught over 2, right? A naught is just a number, okay? We are using A naught for as a, like a general representation. So A naught is any number. Like you can take, let's say, you can take A naught as 100 grams. So we have 100 gram now. After 29 years, amount after 29 years will be half of 100, which will be 50. Okay, now in this case we have A naught as our original amount. So the amount of strontium 90 after 29 will be half of A naught, which is A naught over 2, equals to A naught as it is e to the power k times 29. So our target is finding the value of k. Okay, we are trying to find the value of k, and we substitute in this model, and that is our exponential decay model. Our target is finding the value of k. Now, what kind of equation is this? This is a exponential equation. Okay, so we have to solve exponential equation. Now, how do we solve exponential equation? The very first method is we try to make a same base on both sides. Now, what base do we have on the right side? E, right? We have A naught over 2. Now, is it possible for us to make a same base on both sides in this case? So we don't know what is A naught. So it's a general representation. So it's not easy. And if you cannot make a same base on both sides, then what is our next option? We take log on both sides, right? So before that, let's get rid of A naught. So let's divide both sides by A naught. So we make exponential expression by itself. So this A naught cancel. So A naught cancel. So we have 1/2 on the left, e to the power k times 29, 29k. Before you take log on both sides, you must have your exponential expression by itself. Now we can take log on both sides. Now what log do you want to take here?
The 29 or the 1/2?
No, so you have the option here. So taking log means you apply common log on both sides, or natural log, or log to any base. So taking log means you are writing log in front of this expression. Now we have these options. So what would be the best option for us here? ln, right? And the reason here is that our base is e. So just take the log with a base given to you. It will be easier for us to simplify. Okay, so here base is e, so we will take a log with a base e on both sides. It means you are writing ln on both sides. Okay, so we have ln here, we have ln here. That's what it means by taking log on both sides. Okay, you can take common log, it does not matter. But if you want to make it simple, just try to take a log with the same base on both sides. Okay. Now here, let's simplify our right side. So on the right side, we have exponent. So we have 29k as exponent, and we can remove this exponent by writing in front, right? So we have ln of 1/2 equals to 29k ln of e. Now what do we know about ln of e? What is the value of ln of e? It is 1, okay, because ln has a base e, so ln of e to a base e is 1. Our target is finding the value of k. Now let's divide both sides by 29. So ln of 1/2 divided by 29 is our k. And if we use calculator for this expression, we get negative 0.0239. So this is our value of k. And if you need help in getting this number using your calculator, let me help you, okay? Make sure you put parentheses for 1/2. So type ln, okay, make sure you are using ln, parenthesis 1/2 divided by 29, and you must get negative 0.0239. Now we go back to our function or a model and substitute k, and that is our decay model, okay? So our final answer is a of t equals to a naught e to the power k is negative 0.0239 t as it is. So this is our decay model. So this is our function that give us the amount of strontium at any time period. Now, let's say, for example, we have initially, so our initial amount of strontium is, let's say like we have 100 gram, okay? Now, can you find the amount of strontium after like 10 years? Can you find this? So let's say we have 100 gram of strontium-90, the radioactive element. Now it does break by itself, okay? That's its property. Now what will be the amount of that strontium-90 after 10 years? And that can be found from this function, okay? So we know our initial A0, initial amount of strontium is 100 gram, okay? So we use that model, okay? We use this function. So our target is finding the amount of strontium when our time is 10. So initially we have A0, which is 100. So we have 100 gram times e to the power negative 0.0239 times our t is 10. Okay, so this is 100 e to the power, let's see. So this number times 10 is negative 0.239. Now can you help me here? Can you find 100 times e to the power negative 239? What is this equals to? Can you help me here? So we have 100 gram initial strontium-90. And our target is finding that amount of strontium-90 after 10 years. So what will be the amount of strontium-90 after 10 years?
78.74.
You say 78.74 gram. See, so the 100, so we had 100 gram, and after 10 years, we still have 78.74 gram. Okay, I mean, using this function, you can find the amount of strontium-90 at any time period. Now, okay, any question up to here? Now, is it possible for us to find like how long it takes to decay all these 100 gram? Can you just find the time that 100 gram of strontium-90 requires to break into like a 0 gram? How long it takes to break everything 100 gram? Now, what does it mean by breaking into everything means? What will be the amount of strontium 90 at that time? 0, right? So breaking into, say, we want 100 gram to break down. Okay, we want that to go into 0, right? So let's see how long it takes. So we have the same function. Okay, we are using the same function. And we want to find the time, okay, we want to find the time such that that 100 gram breaks into 0, okay, so it means the amount after time is 0. That's what we want to know. So when our amount after t is 0, our a naught is 100, e to the power negative 0.0239 t. So we get rid of 100 by dividing both sides by 100. So this is 1, this is 0. So we have 0 equals to e to the power negative 0.0239 t. Now we apply log. Now each log of, can you use your calculator to find ln of 0? What is that equals to? Ln of 0. Is that undefined? That's undefined, right? So there is no value for ln of 0. So here, this number is undefined. There's nothing we can, since this is not a real number, we cannot calculate. So here it means like, does it mean that it never decays to 0? Right? So that is strontium 90 that never decays to 0.
Is that a E?
Yeah, okay, yeah, I'm sorry, yeah, that's e. E to the power negative 0.0239, yes. This t is undefined here. We don't know what is t. We can't find because this is undefined. Ln of 0 is undefined, so t is undefined. So it means it never decays into 0. It never breaks down into 0. So if we graph this function, how does it look like? Let's use our graphing tool. Okay, so let me go to here. Our function is a of t. So let me use y for a of t equals to, okay, a naught. I can't use a naught. Let me just use a naught as a 1. So we have e to the power negative 0.0239 t. Instead of t, let me use x, okay? Now this is the graph here. So this is the graph for our function. Now, do you see why it's called decay? Because like as the time increases, the amount of strontium, it decreases, right? It goes down like here. So as you move from left to right, our function is decreasing. Okay, so this is the exponential decay. So that the breaking down of strontium 90 is exponential decay. Yes.
What did you put the graph in?
Okay, so here, so I use, so instead of a naught, I use 1. Okay, for a of t, I use y, and for t, I use x. Okay, I'm not sure they have t. Okay, so if I use the same variable here, I may not get a graph here. Okay, let me try that. So I never try. So let a equals to, we may not get a graph here. So e to the power negative 0.0239 t. Oh, okay, we get the same graph. Okay, so it's okay if you use the exactly same variable. So we still get the exactly same graph. Okay, so it's not that we are required to use x and y every time, so it's okay to use any variable. Okay, so this is the one situation where we can use our exponential function. Okay, any question up to here for this example? Okay, now we do have part B here. So in part B, calculate the time required for strontium 90 to decay to 1/10 of A naught. So we want to find the time that strontium 90 required to decay into 1/10 of original amount. So our A naught is the original amount. Okay, so if we are taking 100 gram as our original amount, what will be 1/10 of 110? Sorry, yeah, what will be 1/10 of 100? 10, right? So we want to know how long this element take to decay from 100 gram to 10 gram. Okay, so we use the same model. Okay, so let's use the same model. So our function is a of t equals to a naught, sorry, this is a naught e to the power negative 0.0239 t. We are asked to find t such that amount of strontium is 1/10 of a naught. So we replace by 1/10 of a naught equals to a naught as it is, e to the power negative 0.0239 t. This is the exponential equation. We make exponential expression by itself on both sides by dividing both sides by a naught. So this is 1, this is 1. So we have 1/10, which is 0.1 equals to e to the power negative 0.0239 t. Now, can you find the value of t from here? We have exponential equation. Can you find the value of t? What will be our next step? Yes, we take natural log on both sides. So we take ln. You write ln in front of this expression. ln. So on the left side, we have ln as ln of 0.1 as it is. On the right side, this is the exponent, and we write down this exponent in front of ln. Okay, in front of ln, and we have negative 0.0239 t ln of e, and we know ln of e is 1. Our target is finding the value of t. So let's divide both sides by negative 0.0239, negative 0.0239. So if we divide ln of 0.1 by this number, we get 96.34 equals to t. So it takes 96 years, more than like a 96 year to decay into 1/10 of its original. So if you have 100 gram right now, after 96 year, we still have like a 10 gram left. Okay. So this is how we can use our exponential function in modeling the radioactive decay. Okay, so here strontium 90 is a radioactive element. Okay, any question up to here? Okay, so let's see what we have next here. Okay, now here table 1, okay, we don't have table here, let me draw that table here. Okay, now here I think we need a calculator to find a graph here. So instead of this one, let's not do this one, okay? Because we do have a table, and using the table, we have to find the exponential function, okay? So let's not use this example. Let's see what we have our next example. So in this table, okay, we need a table 4. Okay, we have a table 4 here. So it tells graphing you. Okay, I think we can. So let me draw that table. Let's see if we can find anything here. Here now, there is no way we could calculate the value of A, C, B from hand. It has to be, we need a graphing utility or software, okay? But our function using a graphing utility, so the f of x is 537 divided by 1 plus 1.813 e to the power negative 0.04x. So this is the function, okay? So this function gives the population of South Africa for the selected years from 1970 to 2000, okay? So they have a set of data. They plotted a scatter plot for that data, use the graphing utility, and they have this function, okay? So we are not finding that function, but let's try to use this function, okay? So we have this function, and this function give us the population of South America for selected year from 1970 to 2000, okay? So here x is the number of years from 1970. Now let's use this model. So what is the projected population in 2020? So we have a function, okay, f of x. Our f of x give us the population, okay, f of x give us the population. Do not forget that. Our x is the number of years since 1970. Now what is the question? We are trying to find the projected population in 2020. Now, so let's make a projection for 2030, okay? So instead of 2020. So let's make a projection of population in 2030. Because this is our future. We don't know what will be the population of South America in 2030. Now, at first, you should know we have two variables, f of x, it is the population, x is the number of years. Now, what variable we are asked to find here? From this model, what is the projected population in 2030? So, which variable we are asked to find here? Is it f of x or x? Which variable we are asked to find? F of x represents population, x represents number of years. So, the question is, what is the projected population in 2030? Now, which variable we are asked to find? Is it f of x or x? We are asked to find population, right? So, finding population means we are finding f of x. Sorry. So, our target is finding f of x. So, our target is finding f of x. Now, what about the number of year? So, we need to know what is x. So can you tell me what will be x for 2030? How did we define our x? X is the number of years from 1970. So if x is the number of years from 1970, what will be x for the year 2030? So our x is the number of years from 1970. Okay, like after how many years from 1970 we get to 2030? Is it like after 60 year, right? So our x is 60. So for 2030, our x is 60. Now we replace every x of this function by 60, and that give us the population in projected population in 2030. So f of 60. So let's replace every x by 60. So 537 divided by 1 plus 1.813 e to the power negative 0.04 times 60. Now, can you do this on your calculator? So make sure to have parentheses for your denominator, okay? So type 537, okay, divide by parentheses, and inside the parentheses, you're gonna type all these. Can you do that on your calculator? Make sure to have parentheses for your denominator, okay? If you have more than one term or a negative term, always parentheses.
So do we also put f of 60?
No, do not put f of 60, okay? This is just a representation, like everything on the right. So you start with 537, okay, divided by parentheses, and inside the parentheses, you're gonna type all these. Does anyone have a final answer? 537 divided by parentheses, and inside the parentheses 1 plus 1.813 times e to the power, that's a power, negative 0.04 times 60.
What if like the parentheses go big and small?
I'm sorry?
Like it's not going small on the.
Okay. Let's see if I can use my calculator here. Also, okay. Okay, so what number we had in numerator? 537, right? Divided by parenthesis 1 plus, can you read after what we have after 1 plus?
1.8
Is it 1 point?
or 1.8.
8,
1,
1, 3.
3, e.
Okay, so we e to the power, right? So power
Negative 0.04.
times, oh, okay.
60.
Okay, now we have to multiply that one. So we might need a parenthesis here as well. So parenthesis negative 0.04 times 60. And parenthesis close. Now I think we should get, yes, 461.15. 461.15. It should be in million. So how? Let's see. Yes. So the population of South America in 2030 will be 461.15 million. Okay, that's our projection. That's what we can find. We can project using this model. Okay, so we use this kind of mathematical model to make a projection. Okay, but it's not, we may not be 100% true. The population may not be exactly 461, but this is what we can make an estimate. Okay, any question? So whenever you have a word problem, so you do not need to scare. Just try to identify what is given to you, and you should know what is asked. And once you know what is given and what is asked, the remaining is substitution and simplifying. Okay. Now let's go back to our the second example, and let me see if they have a function to use for us. Okay. So we are not finding a function. Okay, we do have a function here. So here we have a f of x for a national debt. Okay. 461.15 million.
Oh, I can't see that.
So this is the projected population for the year 2030. So here we have f of x, okay, equals to our function is 681.2 1.093 to the power x. Can you tell me what type of function is this? Is it a log function or exponential function? Exponential, right? Because our input is in the exponent. Now here, what does f of x mean? So f of x is the United States national debt in billions, okay? So f of x is the national debt in billions. Now what about x? So how they define x? Okay, so let me go back. Okay, they didn't define x here. So x should be number of years since 1975. Okay, x should be number of years. So x is number of years since 1975. Now let's do second part. Okay, what was the estimated national debt in 2010? Now we have this function. Okay, so here we have two variables, f of x and x. F of x, it gives us the national debt. Okay, it gives us the national debt. X is the number of years since 1975. And what we are trying to find? We are trying to estimate national debt in the year 2010. Now, from here, can you tell what variable we are asked to find? Is it f of x or is it x? What was the estimated national debt in the year 2010? Now, are we asked to find f of x or x? F of x, right? Because f of x is the national debt. We are asked to find what was the estimated national debt. Okay, so our target is finding f of x.
What do you put after years?
Since 1975. Okay, since 1975. So for part B, our target is finding f of x. Now, if we are asked to find f of x, x must be given to us. So let's find out x. So what will be x for the year 2010? How they defined x? X is the number of years after 1975. So we are talking of 2010. So what will be x for 2010? So from 1975, after how many years we get 2010? How do we find that? You take the difference of 2010 and 1975 and we get 35, right? So our x is 35. Now let's replace our every x by 35. So f of 35 equals to 681.2 times 1.093 to the power 35. So use your calculator and we get 15,310 billion dollars. So that will the estimated national debt in the 2010. So this is $1 billion. So this was what they estimated from this function, and the actual value was $13,000. $13,000 billion national debt in 2010 of the United States. Okay, so this is what we got from our function. Okay, so this was the estimate, but the actual in 2010 was 13,000. So it's not that we get the 100% the fact. Okay, we get something close. Now, can you estimate the national debt for our next year 2016 using this model? Can you do that? No, so this is the final answer. Okay, so you multiply 681.2 times 1.093 to the power 35, and this is what we get. Now the question is, if this model is true, okay, now this is the function they created with the help of data, okay, so it's not a random function. Now can you estimate the national debt of United States for our next year 2026? So how do we do that? So we want to estimate the national debt for 2026. We don't know. Let's make an estimate. Okay? So we are estimating national debt means we are finding f of x. So what will be x for the year 2026? 59? 51, thank you. So our x is 51. So now you replace every x by 51. So f of 51, you are taking the same function, 681.2 times 1.093 to the power 51. To the power 51. Now can you help me here? 681.2 times, make sure to have parentheses for 1.093 times to the power 51. Does anyone have final answer?
It's 63,518.
63,518.
Yeah.
Wow, that's the national debt that we will have in next year. $63,518 billion. Do we know what is the current national debt of United States? Let's Google it. Okay, let's see. Let's find out. Are we close enough? $38 trillion. Okay, that's the current 38 trillion. So we have like 63. That's a high. We may not have this much debt in our next year. And we don't have that much time, right? We just have like a 1 month. But it's an estimate, okay? So it's not that we always get 100% fact, but we can make an estimate. So this is how we can use our function or different model in our real life situation, okay?